So here's what we're doing.
I have one of those.
Quickly review. Got a couple YouTube videos today.
Yay.
I'll do the best talking about the atomic models. Alright, who wants to summarize what they put?
I got it.
You got it, Gage.
Well, I don't know how to say the first guy's name, but he was basically he was just a philosopher, thought he knew everything, was just saying stuff. He was sometimes speaking truth, but he didn't really back it up by experiments. Dalton came to his conclusions because he was studying gases and actually had things back up what he thought about them.
What is Dalton really known for kind of spearheading? What law? Well, relative masses, but he was also pretty influential in coming up with a law. What was it?
The law of definite composition.
Yeah, what is the law of definite composition? I mean, kinda. I mean, essentially he said that when you have a compound, you always have the same amount of atoms for that compound. Like for H2O, for a water molecule, you always have 2 hydrogens and 1 oxygen. Now, he knew that because he studied relative masses and started breaking up various compounds and seeing how their mass ratios compare. And no matter what amount of mass he started with, he always got the same ratio for each compound between the atoms that made it up. Okay? What about their actual picture models? What do they look like? If you were to draw a picture of these guys' models, what would it look like?
Dalton's was the plum pudding.
No,
that was
today's.
Thompson's.
That's coming today.
Oh, yeah, these are
I mean, you got a picture right there.
Dalton's was just dots.
Yeah, they're just. Remember, he thought that they were just solid spheres. Okay, I'm not 100% sure Democritus had much of a model, but if he did it, it was very comparable to what Dalton had. Okay? Any questions?
What page is this on again? 73.
It's all like.
There's the one picture of Mr. Dalton's model. Okay? So here's what we're going to do today. We're going to continue talking about, I think, the 2 biggest findings in the process of these atomic models. Because up to this point, we really don't have, at least from a model standpoint, much of anything that compares to what we have today, right? We know that, have any of the subatomic particles been introduced yet? No. Okay? So today we're going to talk about 2 more models. We're going to talk about J.J. Thomson's model, we're going to talk about Ernest Rutherford's model. Okay? These were pretty big deals back when they were going through this stuff. J.J. Thomson was known for discovering the first subatomic particle, which is the electron. We're going to watch a couple YouTube videos, how he did it, and things like that. Pretty cool. And then my favorite experiment is the Ernest Rutherford gold foil experiment. I think that was just phenomenal. For one, it kind of blows my mind. I think you can shoot really small particles through things that look solid to us. Like if I had an alpha particle shooter, I could shoot right through that wall, no problem. Because at a subatomic level, what is going on? Yeah, most of the atoms what? Open space, right? You got the nucleus, which is the really dense part, and then you got this big open space with electrons flying around it. So most of the atom's volume is simply open space. Now, can we see that? No.
Is that why the outside temperature affects the temperature in here so much? Like if you were to shut off like the heat or the air conditioning?
I don't know about that because that energy can transfer through. I don't think and maybe it's because of the air between them, but usually air is a good insulator. So I don't know if I can make that necessarily connection. Okay? So first model we are going to go over is Mr. J.J. Thomson's, and I'm going to come back and kind of go over this. The video does a really good job of explaining it. So, all right.
about atoms kind of like this. They're made up of a variety of smaller subatomic particles. But in the late 1800s, it was all about John Dalton's model of the atom.
Is that good enough for any
In
bolt
the
lights?
early 1800s, John Dalton had proposed that all matter, all stuff, was made up of tiny, indivisible particles called atoms. At first, not many people believed him. But throughout the course of the 1800s, more and more scientists got on board with his idea. But it remained an open question
You hear it fine?
whether the atoms were really indivisible. Were they like tiny little billiard balls, hard and solid? Or were they made of smaller things? No one really knew the answer to that. But J.J. Thomson was able to answer part of that question when he discovered the electron. He discovered that it was much smaller than atoms. He discovered that atoms had electrons. And so he was able to say for the first time that atoms weren't totally solid and indivisible, but they were made up of smaller, subatomic particles. Let's look at how he discovered the electron. So Thomson used what's called a cathode ray tube. It's a big tube of glass that's kind of like a bottle. You can imagine it's sort of like this soda bottle. It's sealed all over, and then you pump all the air out of it. Okay, and it has these two pieces of metal at this end. So Thomson connected these two pieces of metal to a power source, and here's what happened. A ray shot from this piece of metal across the tube and created a glowing spot over here when it hit a special coating on the inside of the glass. Now, Thomson didn't know what was going on, but what really was going on is that electrons from this piece of metal were shooting out. They were attracted to this piece of metal, which has an opposite charge, but they were moving so fast that they shot all the way across the length of the tube. Anyway, Thomson sees this ray, and he gets curious as to what it's made of. And so he asks the question, the stuff that the cathode ray is made of, does it have an electrical charge? And here's how he attempts to answer that question. He takes two metal plates and puts them on either side of the cathode ray tube. And then he turns on electricity, which makes the top plate positively charged and the bottom plate negatively charged. And check out what happens to the cathode ray. When he turns on the power, he sees that now instead of going straight through, the cathode ray bends up. It bends up towards the positively charged plate. So based on this, he reasons that the cathode ray must be made of stuff that's negatively charged, since it's attracted to the positively charged piece of metal, and he knows that opposite charges attract. But just because he wants to be very careful, he's a very careful guy, he tries to check this another way. So he uses a magnet. If something has an electrical charge and it's moving, a magnet will push it in particular directions. So he takes a cathode ray tube, if you want to think that this marker is kind of the cathode ray tube, and he surrounds it with a magnet, just like this. We can kind of show what goes on by slipping the magnet under like this. So anyway.
The reason why I'm showing you this video and not explaining is because he's got really good visuals. I can't draw that well.
The cathode ray bends in the other direction. It now moves downward. Now, if the cathode ray is indeed negatively charged, this is exactly how you would expect it to move in the presence of a magnet like this. So this is just further confirmation that whatever makes up the cathode ray probably is negatively charged. So he takes the data that he gets from these experiments, and he's able to draw a few important conclusions about cathode rays and what makes up atoms. Okay, so based on the outcomes of the experiments with the charged plates and the magnet, Thomson is able to conclude that cathode rays must be made of stuff that is negatively charged. Okay? he combines the information that he got from the experiments that I just told you about with some other data that he collected. And he's able to come to the conclusion that the particles that make up cathode rays are 1,000 times smaller than a hydrogen atom. Hydrogen atoms are the smallest atoms. So this thing that's in the cathode rays must be really, really tiny compared to an atom. And finally, Thomson swaps out the type of metal that's in the cathode tube. He uses a variety of different types of metal, but he finds that all of the different metals he uses give off the same cathode rays, and regardless of what metal he uses, the size of the things that are in the cathode rays is exactly the same. So based on these three conclusions, he's able to come up with the idea that atoms have tiny, negatively charged particles inside them, and these things that we're talking about here are electrons. Now, if you're like me when I first learned this, you might be confused how these conclusions definitely tell him that there are electrons inside atoms. I remember when I first learned this stuff, I was thinking like, wait, doesn't this just show that electricity or cathode rays have negatively charged stuff? How does this tell us anything about the atoms? Okay, here's why. At the time that Thomson does his experiment, everyone, for the most part, agrees that all things are made up of atoms, that atoms are the smallest things that make everything up. They're like the smallest things in the universe. So if Thomson is able to show that there are even tinier things, well, where are those tiny things coming from? They have to be coming from atoms because everything's made of atoms, right? That's the only place they can be coming from. And even if electricity, even if you want to say that, oh, well, he's just showing that electricity is made of electrons, well, then still, where are the electrons coming from that make the electricity? The electrons have to be coming from other atoms. And since he can remove these pieces of metal and swap other metals in, and he still gets electrons, it again shows that all different types of atoms are able to release or give off electrons. So they must be in there to begin with. Anyway, these conclusions that Thomson comes to have dramatic effects on how scientists think about what the atom actually looks like. Now, at the beginning of the video, we said that in Dalton's atomic model, atoms are indivisible, that they're not made of anything smaller. But when Thomson discovered that atoms have tiny negatively charged electrons inside them, he essentially disproved this model, at least the part about the indivisible atoms. So here is the model of the atom that Thomson comes up with. He realizes, first of all, that electrons are negative. We already talked about that. But then he notices that on the whole, atoms in general are usually electrically neutral. So even though they have these negatively charged electrons inside them, the atoms as a whole don't have charge. So Thomson realizes that in order for the atoms not to have a charge, there must be some positive charge in the atom that can balance out the negative charge of the electrons. And then the positive and the negative balance out, and the atom then as a whole doesn't have a charge. So he comes up with a model that he calls the plum pudding atom. Now, plum pudding is kind of a British thing, so if you're American, it might be better for you to think about this as like the blueberry muffin model. And here's how it works. Thomson imagines that the atom is like a blueberry muffin, and that electrons are stuck in this atom the way blueberries are stuck in a blueberry muffin. So you have these little electrons that are stuck in the atom, but then they're surrounded sort of by a dough. And the dough, like in a blueberry muffin, keeps these electrons or blueberries held in place, but the dough itself has a positive charge. And it's that positively charged dough that is what balances out the negative charge of the electrons. And so together, they don't have any total net charge. So the atom is electrically neutral. So that's how J.J. Thomson.
Alright, I think that about covers that. Questions? What do you think?
This is probably a really stupid question.
Yeah.
But, okay, so.
Sorry, I mean, not yet, it's a stupid question. Go ahead.
He was just shooting electrons, right?
Yeah.
How does that work if they're.
He wasn't, so essentially what he was doing was taking a battery and applying a high voltage to a metal plate. And what that did is stripped electrons off that cathode and shot them through.
So then if the electrons left toward the positive charge side, would the protons and neutrons go to the negative charge side? Or is there?
No, the only thing that moves are electrons. Protons.
That's
can't
right,
move.
that's right. That's
Yeah.
like, oh, yeah.
Because those electrons are outside the nucleus and they're flying around and zipping around, they have the ability to be stripped away and sent
But like-
somewhere else.
No, that it probably would like the electrons go this way, like the. So he was the first to come.
Yeah, I mean
That's so cool.
it's crazy. I mean, he kind of explains it like. Well, I had another video that was talking about how literally this guy sat in a dark room and just like waited for like light flashes, like to see these electrons come out the cathode. Which to me, I mean, these guys had a lot of challenges when they were finding these things because they didn't have the resources that we have now. But so they're way smarter than us, yes.
Dude, the spider went down.
What are
But-
we? Do you think we're gonna keep on advancing?
I don't know, man. We're not as smart as we once were. I don't think we might find some stuff,
Well,
but
obviously.
But
okay.
if
Yeah.
we took the electrons away from the atoms, wouldn't that change what they are?
It would make them an ion. Yeah.
I'm so confused how energy is working.
I know. It's so-
Yeah, I
How
know.
do
Just
people-
wait
how
till
do
you get
people-
into the wave-particle duality that electrons can
people
act as a
capture
wave
energy?
and as
Yeah,
a
that's-
particle. And say
This is,
that.
I was thinking that whole video, I'm like, how do I get power to my house and everything? How? Like,
I get.
You create a potential difference that eventually it's like pushing electrons through your wire to your house. And as those electrons go through your, whatever it is that you need electricity for, it does work due to force applying over a
but it's
distance.
gotta start somewhere.
I know, right?
It's like-
But think about this, like a battery, what a battery is actually a chemical reaction that just spits out electrons.
Numbers.
That's all a battery is. So, pretty crazy. I mean, it's a little more complicated than that, but in its broadest sense, yes.
So was it Thomson that discovered that since there were electrons there had to be protons?
No, he did not discover the protons. It actually was, I can't remember if it was Rutherford or like a group of people after Rutherford discovered the nucleus.
He didn't discover the
He
protons.
just
He just
had
knew there had to be a positive.
Yeah, so
he
he,
didn't.
He didn't
He
discover
didn't-
the
electron. He just knew that they
He
had
just-
to
he
be.
yes, he deduced that because most atoms appear to be neutral, there had to have been some positive part of the atom. And that's where that like batter that he was saying, that
Yeah.
positively charged, is how he rationalized that.
What happens to the electrons after their protons are? Like, do they go back and find more atoms,
usually-
or are they just chill, or they just go chill?
Great question. I'm not 100% sure. I know that part of that light had to do with energy dissipation due to electrons. We'll talk later in this chapter how a lot of times electrons can be excited to a higher energy level, but they're not stable at that higher energy level, so they'll go back to a lower energy level and emit their energy in the form of light. That's what fireworks do. And if you guys remember in physical science, we burned all those salts. Same idea.
Can we do one of those kind of experiment like that?
Are you
I feel like that's the best way
Also,
to finally understand.
He took the air out of the whole thing.
I'll look up what it costs to get a cathode ray experiment, but I have a feeling.
We
it's
just make our
probably-
own.
It just said you
Just
need a
make
little
our own,
plastic.
yeah.
and
Yeah.
then water.
Gotta wash.
Yeah, vacuum.
Just a-
I mean, I could get something that could create a vacuum. That wouldn't be that difficult, but.
The back.
That's all you need.
That's,
You need to put little metal plate.
yeah.
I also have, he has a, first of all, that vacuum isn't 100, it isn't 100% airtight. There are some gas particles in there, and that's what led to actually the fluorescent glow that it had. But he broke, what we're talking about is actually still a very, very low level of explaining that. Like, there's a lot more that goes into that than
Trying to dumb it down.
I mean, yeah, I mean, I even need it dumbed down to, you know, I'm not saying that I have all of that stuff figured out either. But it is a very high level idea. Okay, let's progress. We don't have a ton of, I want to make sure we can get through the second one. But I think you guys probably got the point, you know, what he did, how he concluded those things, and then his model. So I don't think I'm going to hit on those anymore. Okay. Rutherford. What he did is he took this J.J. Thomson's model, and he's like, okay, I'm going to do some more studying on this just to make sure that this is true. And he started to do his infamous gold foil experiment. Now, first off, alpha particles, what alpha particles are, would be like, after you've taken away a bunch of the electrons, that's what's left, positively charged ions. You can actually accelerate positively charged particles too. They do that all the time in particle accelerators. Big, like, hadron collider machines where they actually like shoot these particles at objects and deduce what's going on inside the object by how particles scatter off of it. And it's great. I mean, it's just such a high level material that
Wait, so are alpha particles basically just like big cations?
I wouldn't call them big, but yeah, cations.
Wait, so 73 electrons would.
This is just saying that proton, like, essentially, we know that electrons are really small. So what this is saying is the positively charged with the neutrons and the protons in the nucleus with very little electrons in it is going to be a lot more massive than.
So it's like just a little bit bigger than a normal atom.
It'd actually be smaller than a normal atom. It'd be what the atom was without the electron.
Okay.
Okay? Alright. Not that one.
But so it doesn't have that many, it's just that big.
Hey, Mr. Kramer.
That's just showing you the comparative mass, like how much more massive it is than the electron. That's all it's saying. It's not saying it has that many electrons in it.
Yeah.
Okay? Because we talked about how really the electron is significantly smaller in mass than even the proton and the neutron themselves. Does that make sense? So
So the electron's the smallest thing.
no, they believe that actually protons are made up of even smaller particles now.
But
Quarks is what they're called. Yeah. I mean, I'll be honest, I don't know very little about quarks. I actually think if you want to learn something fascinating that I think is just mind-blowing, you think this stuff's mind-blowing, YouTube or Google how the nucleus is held together. Because what's inside the nucleus? A whole bunch of positively charged things. Don't they repel?
What?
So, I mean, that is mind-blowing.
So wait,
Wait, no.
maybe the neutrons are much bigger, and like they have kind of no.
Yeah.
Neutrons are neutral, supposedly. Yeah, so.
Yeah, but then like it's.
And the
could it be
electrons
some-
are orbiting around, like attracted.
But then could it be something like space? Like bigger things have gravity, and the neutron's bigger than a proton, and it's I don't know.
I mean, yeah, we could speculate a lot, but yeah, it's.
Is it because they're like so tiny they have those like little
Alright.
force?
So here's Ernest Rutherford. He discovered the nucleus. I will say there's a couple parts in this YouTube video that are annoying, so you'll know what I mean when we get there.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure this scattering rate as a functional angle. Now, the experiment that he and his colleagues carried out was very laborious, involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back.
Well, this keeps you awake.
Okay.
And it's fascinating, I think, to them that this was telling us something very important we didn't know about the very deep structure of matter. It showed that the nuclear atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing them.
Don't focus on the bell. Listen to what
looking
he's
at the way the particle is scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, it was the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference.
All right. Now, that one wasn't as long, it wasn't like as detailed, but let me kind of summarize this for you. Oh, loud.
That's more annoying than those.
So here's what he did. Remember, he's shooting these positively charged. Think of them as he's shooting cat irons. Okay. I think what they said was it was actually like they were actually shooting like nucleuses of a helium atom. Basically. Yes. No electrons. Okay. So he's shooting those particles, and you saw that gold foil didn't have any gaps in it, right? Okay. And so what he kind of assumed is that, with plum pudding model, it would just go right through, the plum pudding model, because it wasn't a hard sphere. It was more of a soft material that would just kind of go right through. Okay. And what really happened was those alpha particles, most of them were doing what? Going straight through. You saw that one detector had what? A million some. And it was just going like, what do you say, 2,000 a second or something? So those alpha particles were hitting that, going through, straight through that gold foil, hitting nothing, going right to the back and being detected. Okay, and that should make sense based on what we know about the atom now, that most of the atom is what? Open space. So those positively charged particles were going straight through the open space and hitting the back of the detector behind it. However, occasionally some of those particles would appear to hit something or be deflected by something. What it was being deflected by was what? The nucleus, right? And he said it was being deflected by the charge. Well, part of it could have been the fact that it was getting close to really close to the nucleus and just deflecting due to the charge. A lot of it has to do with hitting that really dense nucleus, right? I mean, the nucleus is like the most dense thing we have, like we know of. Okay, so it's like hitting that at an angle and being considered. Now, comparatively, what was like 60 versus like millions? That kind of gives you a big picture of, wow, it really is mostly open space. And that's kind of crazy. All right, any questions about that? Now, he didn't determine that he just discovered the nucleus that there was just some center of positive charge. He didn't identify neutrons yet. He didn't identify protons yet. That comes later by a different guy. And I think Rutherford has a part in that. Like, I don't think that he's totally set apart from discovering the protons. I can't remember, Chadwick or something is his name. Okay? All right. Okay, here it is. A decade after discovering the nucleus, Rutherford identified positive particles in the nucleus. And I don't think he's the only guy that did it. Maybe it was Chadwick who discovered the neutrons. I can't remember. Okay. I think these are the last couple things we have here. This should be review from last year. We should remember what atomic number is. Yeah? Where on the periodic table?
It's the little thing that's up there.
It's the what?
Little number, red number.
Little red number, not the really little numbers, but the red numbers. Okay, that tell you how many protons each of these atoms are, and remember, atomic number or number of protons determine what? Identity. It's really important. Okay, they weren't stripping protons away from these atoms, they were stripping electrons away from these atoms. Because if they were stripping protons away from the atoms, what would that do? Yeah, partly that, but it would definitely change its identity. Okay?
Just a little.
All right? So, just want to make it very clear that, if I've got a magnesium, which we know is going to be neutral in charge for an atom, 12 protons, how many electrons? 12. Right? Shouldn't it be the same if the overall atom's neutral? Okay? Any of these guys. Potassium, 19 protons, cut out 19 electrons. However, can you gain or lose electrons? Yes, we've already identified that pretty obviously. Okay, that leads to what we would call either a cation or an anion.
Wait, but if they're neutral, why does it matter how many are in?
How many neutrons are in there?
Yeah. Because if they're neutral, they're not changing
Neutrons,
the
as
charge.
far as we know, the only purpose of neutrons is weight, mass. Maybe they're discovering that neutrons play an important part in keeping protons staying in the middle, but as far as we know, they don't have a charge, so, yeah. If you're really curious, it is a fascinating thing, the whole idea of the nuclear force. Okay? This is just kind of showing you each of these things that you should already, at least for the most part, know. The one thing you maybe wouldn't know would be how they're mapped. I mean, we know that electrons are the tiniest, but that kind of gives you an idea of how much tinier they are. So really what they did to figure out mass differences is, when J.J. Thomson was putting those charged plates and was seeing how it bent, okay? He did that, eventually they did that with varying different types of particles. The more it bent, the lighter it was. The less it bent, the heavier it was. And they had this huge math calculation that they were able to deduce what they call the charge to mass ratio. And they were able to identify how massive these guys were relative to each other. And that's what that relative mass means.
What are they measuring?
A made-up unit called an atomic mass unit.
Oh,
Yep, and you.
they're
Yep. And you'll find later on in chemistry how this number can be two different things. It can be the atomic mass unit, or the AMU of one lithium atom, or it can be the mass in grams if I have a mole of lithium. So we're going to get to that in chapter 9 near the end of this semester, it's a nice strategic way of taking a unit that we can't really comprehend because it's a really small unit, right? You can imagine how small the unit is that weighs the mass of an atom, right? Really tiny. Okay? Well, how do we deal with that? We can't really comprehend what that's like, and so we know what a gram is, correct? So they use the strategic number called the mole to take this atomic mass number and it'd be the exact same in grams, but on a bigger scale. Anybody know what the mole number is off the top of their head by now? 6.022 times 10 to the 23rd atoms. All right. Any questions? Did you not sleep at all ever, brethren?
I was in bed at 10:30 last night, and then I coughed and coughed and coughed until 1 a.m.
Oh no. I'm sorry.
I just
haven't taken a proton off for the day.
Well, I don't know about that, because I think that's typically what you do when you do nuclear changes, like fission and fusion.
So why did they say there would ever be a lack of an element?
Lack of element.
Like, let's say, for an example, that like everybody would be running out of gold if they just make it.
Well, that would break the first law of thermodynamics.
No, take another atom.
Oh, well, first of all, it's not that's an easy process. And there's a lot of energy that goes into that process. Very unstable and not easily contained. You know, there's a reason why we have nuclear meltdowns every now and then. You know, you make a little mistake, you got a problem. Yeah. I mean,
I did the, do you wanna?
there it is. Wow, while you were watching the video or what? When did you do that?
I did it as I was looking, and then the video was pretty much the exact same thing as the book said, so.
You already read it?
Huh? No, that's the thing, I read it last night, thinking that we were gonna discuss it, I missed the memo that we were supposed to write something down.
Okay. All right, do you see the memo, what you're supposed to do this assignment?
Yeah.